Okay, guys, we have a quick, hopefully, lesson on this. Before we begin, I want you to pause the video, and I want you to think of two numbers, or this is basically a challenge problem here. Two numbers that, when you add them together, gives you 8, and when you multiply them together, give you 20. Now, these can be any numbers of any type. Okay, they could be irrational, they could be rational, could be decimals, could be negatives. The point is, can you find two numbers such that when you add them together, it gives you 8. When you multiply them together, they give you 20. So I'm going to pause real quick. Okay, what I've asked you to do is basically solve this system of equations here. You have two numbers, x and y, they might not be necessarily the same, that add together to give you 8. And two numbers, when you multiply them together, to give you 20. So how might you solve a system of equations like this? Well, in a couple weeks, we have scheduled to solving systems of nonlinear equations, but this is a nonlinear equation right here. One way to do it is to do it by substitution. Okay, so let's solve for x here. We have x is equal to get x by itself, we do 20 divided by y. We had divided by y on both sides here. Okay? Then we take this is the value of x, so let's go ahead and plug that in for x. So we have 20 over y plus y is equal to 8. Now this is a little bit problematic because we have a y in the denominator and a y not in the denominator. So in order to remedy this, it's kind of a trick, but I'm going to multiply both sides by y. So this side is getting multiplied by y, and this side is getting multiplied by y. Okay, on the right-hand side, it's very clear we have 8y. Over here, you have y times the binomial. You're going to have to distribute that. Okay, so y times 20 divided by y will cancel, and we have just 20 here. And then here we have y times y, so that is y squared. Okay, and let's move the things to the other side. We've got y squared minus 8y plus 20, and just moving things around is equal to 0. Okay? Now, if you think about it, this is kind of what we have established already, because now we're going to be thinking to ourselves, okay, what two things, when I multiply them together, give me 20, and add together to give me 8? The issue is going to be, well, that's what we're trying to solve. So I don't think anybody in here could be able to factor this, so we have to resort to the quadratic formula. Okay, so we have opposite b plus or minus the square root of b squared minus 4ac all over 2a. Okay? Plugging in what we know, a is 1, b is negative 8, and c is 20. So we go ahead and plug that in. We have opposite, that's 8 plus or minus the square root of negative 8 squared is 64 minus 4 times a, which is 1, times c, which is 20. All over 2 times a, which is just 2 times 1. Okay? So I know that 8 is hard to see up front here. Maybe I can do a better job here. I'll probably switch to blue if that's okay. Okay. So we have 8 plus or minus the square root of, let's see, we have 64. This is going to be 80. 64 minus 80. All over 2 times 1 is 2. Then I have 8 plus or minus the square root of 64 minus 80 is negative 16. All over 2. Okay? So at this point, we usually go ahead and square root this. But if you notice, this is kind of an interesting trick. If you notice, usually what we have done is we've simplified the radical first. Before we do anything else, we simplify the radical. Can we still simplify this radical? Well, I'm looking at 16 here, and I'm thinking, man, that's almost a perfect square. Let's go ahead and write this a different way. 8 plus or minus the square root of negative 1 times 16 all over 2. Okay? So if I do this, then clearly 16 is allowed to leave. So if I rewrite this over here, I have 8 plus or minus the 16 is allowed to leave and become 4 times the square root of negative 1 all over 2. Finally, we've got this thing happening here. 8 plus or minus 4 and the 2. That should cancel with this, leave 2 here, and 4 here. So we have 4 plus or minus 2 times the square root of negative 1. Now let me pause the video and clear the screen here, because this answer right here is going to be very important. So again, we were trying to find two numbers such that when you add them together, they get 8. Okay? So we've got two numbers here. We have 4 plus 2 square root of negative 1 and 4 minus 2 square root of 1. Okay? Those are numbers, I guess. They have two solutions. So let's see if it works. Okay? So if I have 4 plus 2 square root of negative 1, and I add to it 4 minus 2 square root of negative 1. Remember, these are our two things here, right? Well, what should that give us? Well, I see 4 plus 4. These are common things, right? This is going to be 8. And we have 2 times the square root of negative 1 and negative 2 times the square root of negative 1. And that cancels. So we just have 8. So technically speaking, when I add these two things together, when I add this and this together, I get 8. Okay. Let's see what happens when I multiply them together. Okay? So if I have 4 plus 2 square root of negative 1 times 4 minus 2 square root of negative 1, let's see what happens. Okay? 4 times 4, if I FOIL this out, I get 16. 4 times negative 2 square root of negative 1 is negative 8 square root of negative 1, right? I keep the outside terms. I look at those. I do 4 times 2 and then just kind of treat that thing like it's a variable, right? Okay, then I do this one, and I get plus 8 square root of negative 1. And then here's the tricky one here. We've got 2 times this thing. So these are the same thing, just with a negative. So this is going to be negative 2 square root of negative 1 squared. Right? Basically, we're multiplying these two together. That would be 4. And then we're multiplying these two things together. So let's deal with something first. So see this. This is negative 8 square root of negative 1. This is positive 8 square root of negative 1. They cancel just like before. Okay? So we have 16 here. And then let's take a look at this. This is going to be 2 squared is 4. The square root of negative 1 squared is going to be negative 1. If I look at this, I think everyone can agree that this makes sense to be negative 1, that they cancel. The square root and the square cancel. So this is going to be, this negative 4 times negative 1 is going to be positive 4, which means the answer is 20. Okay, so what does that mean? That means that this number, these two numbers I should say, satisfy what we were looking at here. Okay? And so what happened in math is that people started noticing that this was a trend. They would always ask questions like this. It's very similar to what I asked at the beginning. I said, find two numbers where if you add them together, they give you 8, and multiply them, they give you 20. It was kind of like a nice little, fun puzzle way back when, 500 years ago. But some of them didn't have solutions, quote unquote, and they started noticing this. Well, it comes into play when, and there's a YouTube series on this, when we start talking about cubics, because cubics look like this in general. Okay, we know what quadratics look like. They look like a up or down bowl, right? Cubics look like this. The nice thing about these things is that no matter how you draw them and how funky they get, they're always guaranteed at least one x-intercept. So what happens is we have parabolas that look like this, that don't have any x-intercepts. And that kind of behaves like part of a cubic, right? But the nice thing about a cubic is that the cubic will always have at least one x-intercept. It will always have at least one because of its shape, right? And what they discovered is that they used numbers like this. If they used numbers like this, they were able to factor out the important one, the real solution, they called it, right? The real answer, okay? And so we were looking at this thing, and this is the serious issue that mathematicians had. It was the square root of negative 1. Because there is no number such that when you square it, it gives you negative 1. So what they basically had to do with this was they had to say, we have to invent a number so that this math works here. Okay? This math right here has worked every single day. It's very easy to verify if something is a root. You plug it in, it gives you 0. Okay? So they knew that this scary method worked when you're dealing with square roots of negatives, but they didn't know what to do with it because there is no number such that that exists. So they kind of shrugged their shoulders and said, okay, what if there was a number such that when you square it, it gives you -1? And we'll call that number I. Okay? And this guy right here, this was the first what we call imaginary number. Okay? It doesn't exist on the real number line. Remember, the real number line is ordered. You could say, okay, where is 3? Where is pi? Okay? Pi is a little bit bigger than 3. Okay, what about 2.5? Where does 2.5 fall? 2.5 falls before this. What about -7? Okay? It has an order to it. This guy is not part of that order. You can't say that I is bigger than 5 or less than -2 or something like that. It does not stand on this real axis at all. Where it does exist is something called the complex plane. Okay? So if this is the real number line that you know and love, right? Here's 0, here's, 3, here's -2, things like that. The imaginary numbers are actually going to be perpendicular to them, to the real number line. Okay? So here's our friend I that I just told you about. Here's 2i. Here's -I. And what's neat about this number, I, is that there's a lot of math that just works beautifully because it exists. Okay? So it's funny that we say this. We use this term real to describe the numbers that can be produced by a calculator. Okay? If you go to your calculator, type the pi button, hit enter, it'll give you 3.1415926 and some approximation afterwards, right? That's a real number. But I can't be done in a calculator. I exist outside of the real numbers, what we call the imaginary numbers. So what's funny is that I can laughingly say I is not real, but it exists. Okay? It exists in the realm of mathematics. And if there's anybody in here who wants to be an electrical engineer, you use I a lot. Of course, it's funny because when they switched over to electrical engineering, there's already something that stands for I, it's current, so they have to use J. But it's the same value. When you square J, it gives you -1. Okay? So, the cool thing about this is that this is the only rule that you really need to know. The one in the box. I squared is -1, because the rest of the math that we do with these so-called complex numbers, as you have watched in the other video in theory, are of the form A plus BI, where A is a real number and BI is the imaginary number. So a complex number is a sum of real and imaginary numbers. And as far as you care about, this is the biggest realm of numbers that you'll ever have to deal with. Okay, unless you get a master's degree in mathematics, you will never have to learn about a different type of number. But what's cool is that this whole thing stems back to something from way back when. Okay, when you were in first grade, you were told, okay, all the numbers that you care about are the counting numbers, right? 1, 2, 3, 4, 5, 6, 7, 8. They didn't even teach you the concept of 0 because 0 is such an abstract idea as a number. Okay? Then you learn about the whole numbers, you learn about 0. You were never told something to the effect of 2 minus 5 was a real thing, because you can't, if you have 2 apples and you subtract 5, well, it doesn't make any sense. Then you learned about negative numbers, and then the whole thing of dividing numbers, right? You said 5 divided by 2, ooh, can't be done. We can't divide 5 evenly by 2. Then you learn about the rational numbers and realize that could be a case, okay? So complex numbers are the biggest set of numbers that you will ever have to deal with. All numbers that you have learned up to this point, including this guy, is a complex number, okay? All numbers that you've dealt with are complex. It's very hard to come up with one that is not a complex number. I could give you one later, but for all intents and purposes, all complex numbers look like this, because any real number can be written like that. Okay? 5 is a complex number because this is a complex number, right? So, hopefully that makes sense to you. It's a very frustrating subject to say, okay, we're talking about imaginary numbers because they feel like they don't exist, but they do exist. They're just not real.